So first, we're going to talk about give an introduction. What is a support vector machine? And then we're going to talk about how do you solve these problems, and then talk about generalize to a nonlinear classifier using something called a kernel trick, and that will be later part of that. But first, today we're going to talk about support vector machine itself. So support vector machine, and you can view it as a linear classifier. So this goes back to the questions we proposed a while ago. And suppose you have these two groups of data sets here, and one shows on the left side here. The data set is the same. However, I have two different classifiers here. And one classifier is this one here, and the other classifier is this one here. You have two different decision boundaries. The question is this: which one is better? Which one is better? And then we talked about last time, we said, well, we will prefer the one on the right side of that. And the reason why this is the case, because we thought, well, if I could imagine I can collect some test data sets here, something like this guy's here. And then I have other test data that look like this guy's here. Something like that, like a neighborhood, small perturbation, surroundings, labels of that. And if that's the case, you can see that the classifier on the left side will fail on some of this test data sets here. And however, on this right-hand side here, it still has no problems on the right-hand side. If you make small perturbation data points here, the classifier on the right-hand side can still classify without any problems with that. And then for that reason, we believe, intuitively speaking, the decision boundary on the right-hand side is better. Right. So the question is, how do we do this one here? And previously, and we say that what we do is we can formulate some loss functions. Some loss function such that we encourage this type of solution than this type of solutions. And the loss function we introduced for the binary classification problem using such as the cross entropy, the loss function. And you in fact can show that this type of solution will have a lower cross entropy than the solution on the left side of that. So for that reason, if you use the cross entropy, we'll prefer this type of models. So that's good, right? By using this type of loss function, it somewhat provides you a solution here, but didn't address the question, but didn't directly address this question here. So I would like to directly address this question and say, given these two solutions here, which one is better? And then can I come up with a metric to say which one is better? So that's something what this SVM model is trying to do. So one possible answer is this: SVM model is trying to say, and using this project here, trying to say, once I have the decision boundaries here, I want to roughly have some idea is this, what is this gap between these two groups of data points here? So there's one group of data points here, this is another group on here. What is the gap between them? What are the distance that's separating, maximally push these two data points away? And so this is something called margins. So we're going to talk about today how to calculate this margins, and then think about how to optimize it. All right. So that would be this slide's goal is here is try to think about the concept of margins here. So for that purpose here, we're going to change the notations here, because in the SVM, we use slightly different notations here. So that's previous notation, right? We use the parameter theta, and then we have the intercept bias theta 0 and theta and so on. So we're going to change that to a new notation here to be B to be the bias term, and then use W1 to be the coefficient. The reason we do that is because for some reason, historically, in the SVM, people use this WB notations for that. So you can also write down them in terms of vector representation. So that will be W dot X here. So the inner product between W and X plus this bias term B. So the parameter will be both W and B. So within the SVM, we treat them, explicitly separate them here. So in our previous model, we merge theta 0 with other parameter. And we say we don't need to address them explicitly. However, in SVM, we do consider them completely separate, deal with them kind of separate. So that's the reason we try to emphasize using this notation here, right? So in the models right now, previously we have said, we're going to calculate this linear response here, depending on whether this is a greater than 0 or less than 0, we're going to classify and label to be 1 or 0. And within SVM, we're going to using this +1 labels, if this is positive, and use a -1 label if this is negative here. And so that's the another notational change we're going to use for the SVM models here. So if this is less than 0, we say it's labeled -1. If this is greater than 0, it's labeled +1 here. Yeah. So in this type of linear models here, and we know there's one thing here. There's this kind of there's this redundancy in the model. So what I mean the redundancy model here is this. Well, I have the Wx plus b here. Suppose now I double the values of W, double the values of b. Will that change my classifier? Well, if I do that, if I'm going to do 2 times this guy's here, 2 times this guy's here, 2 times this guy's here, you can see that it does not change the decision process here. And if you double the values of W, double the values of B simultaneously, the decision still stays the same because I only look at the values greater than 1, greater than 0 or less than 0. And for that reason, this WB here, there's a redundancy in these parameters here, and it's not completely determined. And for that purpose, I'm going to fix that. We're going to fix those redundancies here by requiring and something like this. So we're going to have this models here, W equal to W dot X here plus B. However, we're going to say this. For all the dots, that is on this positive region here, we require them, this linear things here, to be greater than 1. On the other hand, if this numbers here is on the negative labels here, we require them to be less than -1. So that's the difference here. We're going to use +1 and -1, fix these 2 values. The reason we fix these 2 values here, such that this WB exact numbers is going to be fixed here. We do not have this scaling redundancy anymore, right? Because previously I can multiply by a constant positive number that does not change my decision. And I want to remove this scale invariance here by using this trick here. It's saying this, well, I have this fx equal to 0, but I want to make sure that all the data labeled with +1 here has values is going to be greater than, so in this case here, W dot X plus B on this side here will be greater or less or equal than 1. So that's one side of that. Dot X plus B is greater or equal than 1. And then this side here will be, say, if your data is on the label with -1, I want to make sure all of them to be W dot X plus B is less than -1. So that's the only difference I'm going to introduce here to remove this scaling invariance for that, okay? Right, so, but the problem stays the same here. So I have this parameter Wx. I want to make sure that for all the data labeled with 1, I will make sure that they are above this plane here, this planes here, above this planes here. So I'm going to call that red planes here. I want to move this guys here. And then for all the data that's to be labeled with -1, I want to make sure they are below this place, less or equal than -1. And this is a set of the problem here. No, I didn't do anything, anything new here. The only thing we use this fix to be +1, -1 to reduce redundancy. This one choice of 1 is not important. You could choose 1 here to be 2, and it would be greater than 2 or less than 2. That's okay too. However, just for the convention here, we choose to be 1 here, greater than 1 and less than 1, okay? So that's what we're gonna do here. So next, what are we gonna do here? We're gonna calculate what is the margin between these two lines, 2 separating lines here. And we're gonna say what's the distance from this point here to here. And this is, again, this is the kind of a concept of separation between these 2 group of data points. And that's what we call the margin. We'll calculate these margins here. And how do you calculate these margins here? Well, so that will be involved a little bit of geometry here. So I'm going to go through them here. So right now, remember that this lines here is described by this guys here, by W dot X plus B equal to 1. This is this separating boundary, separating planes here. And this guys here is described by W X plus B equal to -1. So this is all the dots located in the dashed line, in the blue dashed lines here, is going to be described by this. And now we want to calculate the distance between these two planes. So these two planes are only shifting from one side to the other side. So they're parallel to each other. And so that when you have parallel planes, you can calculate the distance between them here. And that is the margin we can try to calculate here. First of all, let's determine what is this direction. Suppose I want to go from this to here. What's the direction what is the direction that is perpendicular to this plane here, to this line in 2 dimensions? In 3 dimensions would be a plane. What is the line that is perpendicular to this line here? Well, what do we know this, right? If you look at this data set here, if we take 2 data sets, this is w dot x plus b equal to 0. And we know that this w here is a normal vector. If you learn from the geometry, that normal vector w itself is perpendicular to this lines because it's normal vector. The reason you can actually show it, how do you show that? Well, you take 2 dots from this planes here, and one is x here, the other one is x prime. 2 of them here, one is x prime. They are here. This is x, this is x prime here. So now you can see that. Now take the difference between them, you conclude that w times x minus x prime is equal to 0, which means that w is orthogonal to this difference between x prime and x here. And that's reason w is a normal vector, is a vector perpendicular to the boundaries of that. All right, so that's first thing I want to do here. So I know whatever the boundary I want to draw from here to here, and then that is going to be along the directions of w. So that's the first thing I want to do here. So let's do this one here. Along the directions of w. So that's good. So next thing I'm going to do here, let's suppose I pick up 2 points here. Pick up, say, I call that, let's see, I call it x minus here. I call this data set x minus. Arbitrary from this point here, x minus here. I call this data set here, I call it the x plus. So I'm going to pick up x plus from this two planes here. From this side here, I call it x plus, and this side here, I call it x minus here. And let's pick up these 2 data points here. Well, so I know one thing I know now. So first of all, because x plus is from this wx plus b equal to 1, so I know this w dot x plus b is going to be equal to 1. So that's one thing I know for sure. Similarly, I know that w dot x minus, because minus x is located within this plane here, plus b is going to be equal to minus 1. So that's one thing I know for sure. Okay? So based on these 2 here, and we know that if we subtract them, we know that w times x plus minus x minus here equal to 2. If we subtract these two equations. So, and this guy's here is w plus minus x prime here, and this line's in that. And this guy's here is x plus minus x minus. And then we want to calculate the length of this guy's here. And however, let's check here. Let's assume x plus minus here because it's going to be along the direction of w here, the normal vector of that. Let's suppose this is equal to a factor. Let's say I call that a factor to be r here, to be r times w, because it has to be along the directions of the normal vector, the orthogonal to this guy's, right? But however, I don't know the coefficient r here. That's something I need to determine that. Well, however, I'm going to plug into this equation here, and I can know that w times dot r w here is equal to 2. So which means you conclude that this coefficient r here is going to be equal to 2 divided by the norms of w squared, because the dot product of w with itself is equal to the length of the squares, length of w and square of that. And that's the norm square. This is r. Okay, I'm very close now. Right now, what I have is this. I know the x minus x now is equal to r times this. And the margins here, the margin, so this is the quantity I'm interested in. The margins here is going to equal to the length of the x plus minus x minus here, because that's this guy's here, right? This is the x plus minus x minus here. And that's the length here. And I want to calculate the length. What is the length here? Well, this length here is going to be equal to the R here times length of the W itself. And however, now you can see the W equal to 2 divided by the square of the norm, and then going to times W here, and then you conclude that the margin here is going to be equal to 2 divided by the norms of W. Okay, so that's the key things we want to talk about. So that's what we talked about so far here. The margin here is equal to this quantity. Okay. All right, so that's the math we're going to talk about so far. And then once we have these guys here, and then we are almost done here. So, well, so what we want to do now is this. We know how to measure the distance between these two boundary planes of that. And then we can formulate a new model, try to learn the parameters of this linear classifier. I want to push this boundary as far as I can, But at the same time, I want to make sure that the data points here are correctly separate, which means they are above this plane and below plane for the other class labels. For these reasons here, what we can do is to do this, right? So I'm going to maximize the margins. So maximize the margins. At the same time, I want to make sure that for all the data points here, it can be separated here. So for that reasons here, I'm going to formulate this as an optimization problem. I'm going to maximize the margin. Remember the margin, let's rewrite it again. So margin equal to 2 divided by the norms of W. So remember that's the margin we calculated here. So in order to maximize the margin, suppose I want to maximize the margin over all possible choices of W and B. So that means is equivalent to minimize the norms W squared of that. So you can see that's the case because margin is 2 over W, the norm of W. And then maximize the margin is equivalent to minimize the square of the norms of W. And so that's equivalent statement of that. So if you understand that, and then we are all set, and then say I'm going to formulate this models here to something like this. So instead of, so we're going to minimize this norms W here. So this is norms W. At the same time, subject to a set of constraints here. So these are the constraints. So constraint this. If your label is +1, so we want that data to be above these planes here, and that which means W dot xi plus b has to be greater or equal than 1. On the other hand, if your data here is a negative label, which means on this side here, and that means your data has to be less than -1 because below this plane here. So on the right side has to be this side here, and the blue here has to be on this side here. And these are the constraints of these models here. Okay, so let's think about it. Let's rewrite it again because I don't want to overwhelm you here, but let's rewrite what we talked about so far. I just want to wrap up with this. You can think about it here. So again, so the data we have here, let's revisit that. This xi and yi here. So that's data we have, and now is I goes from 1 to m. So m here. So this data set here, and the xi here is still would be n-dimensional, and the yi here. So now I'm going to use these notations of -1, 1 to enter the labels of that data set. This is binary classification problem. And the model now is this. So again, the model is going to be W dot X plus B here. So that will be response here. And if this guy's here is greater than 0, and then your predicted label is going to be 1. If it's less than 0, your predicted label is going to be -1. So that's the same as what we did previously. The same as previously here. So that's nothing new here. And however, the learning process now is different here. In particular, the loss function is different here. Well, in this case here, the optimization problem is formulated as this. You say, I'm going to minimize loss function. In this case here, the loss function is simply the norms of W here. And what this just means that if you do I equal to 1 and here, Wi squared, and that the norm is W. And minimize over all choice of W and this bias term V here. And that's the same. However, there's a key difference from this and the previous, because there is this constraint. You have constraints we have to satisfy. Subject to a set of constraints. What are the constraints? The constraint is the W times xi, xj here, plus b is need to be greater than 1 if your label j is equal to 1. So if it's above that plane, you want to make sure it crosses the boundary, separating boundary there. And your w dot xj plus b has been less than -1 if your yj is equal to -1 on the other side. And that is the new model we're going to deal with. You can see it's different from the previous model. So the difference here is this. And this problem now is called a constraint optimization problem. So in this problem here, we want to minimize these guys here, but in this case, we're not trying to, when we minimize here, we're not allowed to choose any b and w and b, but instead, the b and w and b here has to satisfy these conditions first. This condition has to be satisfied. Essentially, we're saying within those conditions, within the space satisfy this condition, we're going to pick up the w that is smaller norm of that. So that is constraint optimization problem. And the question is, how do we solve this constraint optimization problem? And that's something we're going to talk about in the next lecture.